My name is Jay Egg. I'm with Egg Geo. I want to really thank IATMO for sponsoring this session of an IATMO RPA, Radiant Professionals Alliance presentation, how cities can use thermal energy networks to cut pollution. Now, we're used to decarbonization. Why does it say to cut pollution? Because it's a different way to say it, and it might have got somebody's interest, because there's a lot of thermal energy network conferences and presentations, not only here, but coming up in the next few months and throughout the year. One of those is coming up in Rochester, and you can see a rig actually, this is Rochester, Minnesota, a rig actually up in front of City Hall there on the right side, and they're drilling an aquifer-based thermal energy transfer system, which means it's an exchanger that goes down into the aquifer, the drinking water aquifer. We're going to talk a little bit about how that works. We're going to talk about how they tie into thermal energy networks. We are so lucky because we have here in our midst two union brothers. We have Jeremy and Bradley, and I think, Bradley, you're from New York, Pennsylvania. Yes, okay. And we have Jeremy from Minnesota. At Jeremy's office, and I don't know if it's in this presentation, he has four, and this is the shop for Local 455 in Minnesota. He has 4 downhole exchangers that provide all of the cooling passively for their shop, because the groundwater is below 50, right, Jeremy? 52, and they use radiant beams, chill beams, to do the cooling in there, and he's getting ready to put in a heat pump to strip the heat out of that 52-degree water and do all their heating too. So what an amazing group we have here. We have some of the most important people in the room. They handle the lifeblood of geothermal systems. We have the CoreChem team over here. Raise your hand, guys. They are specialists in geothermal energy networks, heat transfer fluids, and just thank you for everybody that is here today on this bright and early morning. Thankfully, because of IATMO's amazing production capabilities, this is all going to be live permanently on YouTube, on their channel, online, a very professional production you can share with others who will say, tell me about this thermal energy network thing. You can say, I sat through this at AHR 2024, and here's a video. You can go right there. So this is, I'm going to go to the first one real quick. You can see the little GIF arrows moving through, but really the most important part about what we're going to be talking about here today is this kind of opaque blue and red line. This is the thermal energy network, and you can see it's just moving in a constant loop. And you have all these plug-and-play buildings and heat sources and heat sinks on here, and that is the essence of a thermal energy network. We want something circulating just like the body's blood throughout a city, because these data centers here, these data centers put out heat even on the coldest day of the winter. They will be putting out bucket loads of heat. And these apartments across the street and these high rises and others need that heat. And if you have any doubts about that, the fact is that every urban center of any size is cooling dominant as a whole. And since that's the case, and it really happened when NYSERDA asked us how they were going to be able to heat 900,000 buildings without using any natural gas or any other source of combustion. They said, are we going to have to drill millions of boreholes in the streets and in the green areas of New York City? And we said to them, no. First, use the heat you have. If you look at all the heat sources throughout an urban center, and you can walk outside and look at the skyline of Chicago, and you can see all the cooling towers blowing that steam off. All that gets turned, you notice these don't have cooling towers on. That heat, and you can see this red line here, is getting pushed into the energy network, and that apartment building is sucking up that heat. So all those megawatts of thermal energy being rejected now get to be reused. And the beautiful thing about all of this is you have exactly the same, fundamentally the same infrastructure as you do in a natural gas system, because what do you have? A pipe in the ground. Just so you know, during the 50s and 60s, the United States ran 2.5 million miles of natural gas pipeline throughout city infrastructure and connected to 60 million buildings and residents. This is what the thermal energy network revolution is about now. This is why 3 states have already passed thermal energy network legislation, which makes PSC regulated utilities like Con Ed, FPL, Southern California Edison able to sell thermal energy. And what is that really? Thermal energy is something you didn't pay anybody for, essentially, because nobody paid for the heat that's coming out of this commercial building and going down. We just turned it down and ran it into these buildings. So once again, we got the pipe in the ground with either the geothermal energy network solution or the natural gas solution. And the only difference is this in here could be a furnace or a boiler, but now it's a heat pump of about the same size, handling the same capacity as an equal furnace or boiler. And here on the floor today, this is not in my presentation, if you wonder, one of the biggest questions for this industry has been, well, okay, I can use a heat pump, but they only produce 130, 140 degrees Fahrenheit. Not so. On the floor right now is a company called Oilon, a boiler manufacturer that just started their heat pump line, and this is not preferential treatment because they're the only one on the floor that has this. They have a 1 lift, in other words, from 50 degrees Fahrenheit to 250 degree heat pump. Commercial heat pump. It's about the size of a small pod, you know, like you'd get from U-Haul. It's probably rated at, I didn't even look at the rating, but they have a heat pump coming out that will, a screw chiller that's almost ready to come out that will do almost 300 heating plus handle all the chilled water needs. So the heat pump answers are being brought to bear by the manufacturers. So these two systems are very similar. We're putting pipes in the ground again, but now we're delivering this energy not to a furnace or a boiler, we're delivering it to a heat pump. And you see it right here, a heat pump delivers something very critical in this age of situations where it's getting so hot. I live in Phoenix, 118 degrees is normal in the summer now. And the same thing could be said of Michigan, of New York. Those are hot cities in the summer. Cooling is becoming a right like heating. And as a matter of fact, California is already passing laws that says apartments shall have cooling under every condition, and New York is sure to follow that. So the cooling component of this is coming just in time. And of course, you get hot water from this. And this is a great rendition of an energy network, because you can kind of see at the bottom that these two buildings, this is probably a manufacturing plant or something, they're radiating heat out that can be gathered up and dumped into this energy network, and then these apartments and single family homes can suck up that energy and not have to even you notice that they don't even have boreholes necessarily under here. They're just pulling in the energy from the network. That's the way it's supposed to be depicted at any rate. Here's kind of, this is the first vision of the system that we created for the New York City Commissioners, because they have rivers running through or around Manhattan. They have wastewater. Stripping energy out of wastewater is up to and even exceeding 1/3 of the energy you need for a building for heating. And this is the cool thing about wastewater. Anybody want to take a guess what the temperature of any building is of their wastewater year-round? Any guesses? It's always between 65 and 75 roughly. If you have, we're getting heat out of 50-degree ground temperatures all over the upper Midwest and the Northeast. And if we can get it out of this at a much warmer temperature, it's easy to strip heat out of 65 to 70 degrees, like you see here. And then dewatering. There is a tremendous amount of dewatering. It's depicting the subways here, but as we talk to RPU and as we talk to other folks in Minnesota, for example, where we're doing a lot of work, and you'll hear something about that, there is a lot of dewatering going on. Now that they've controlled over pumping of the aquifers for one pass, you know, whether it's drinking, lawn watering, whatever, their aquifers are recovering, and now they're having to dewater not only subways, if folks have those in their particular city, but basements of buildings. And that's another great resource. Anytime you're moving water, it's called the water, it's part of the water energy nexus. If water is moving, it is a potential opportunity to move energy. And we have Ralph Faria from Multi-Aqua here, and all he deals with is hydronics. His equipment, and he has equipment of all kinds. We called out Oilon, but I want to point out that they have a multi-source unit, which is something the industry sorely needs. It needs to be a unit that's both air source, and we'll show you an example of that in just a minute, air source and ground source, because there are times of year, we call them shoulder seasons, where it's a beautiful temperature outside. It's 70, 75. You want to use that as your heat sink or heat source maybe, depending on where you are in the time of year. Now we're going to Geo 101. I got you hopefully a little bit excited about thermal energy networks. Now we're going to go to Geo 101 and talk about your refrigerator. Refrigerator's a heat pump. Almost everybody that's been involved in this industry knows it. It pumps heat out of the box and down on the ground to keep your feet warm while you're getting your midnight snack. I know I love that feeling on my bare feet. I go, oh, yeah, yeah. So that's your heat pump. It's pumping heat out. That's how it makes this box -5 degrees and this box 40 degrees. It uses the Carnot refrigeration cycle to pump heat, and that's all the Carnot refrigeration cycle is it's the way we manipulate heat, because heat can only go downhill. We got to get it uphill, so we compress it. We compress the vapor, and the vapor, what happens, just real quick for anybody that likes analogies, if I have a cubic foot of air in front of me, imagine a cubic foot, a box right here, and if I compress it to 1/10 the size, it's not going to be 75 degrees anymore. It's going to be 150 degrees. And there's no energy added to that. We just compressed the available energy into a tighter place, and how does thermodynamics manifest that? It manifests it by driving the temperature up. Then when we release the pressure and it comes back open, it goes back to room temperature. And that's essentially what we do in here. That when we're cooling a building, we have to work against 100-degree outside air, right? So that compressor has to drive up that 75-degree or 80-degree return air. It takes that available energy and it drives it really high, about 150 degrees. So when your outside condenser unit blows air over those coils, the 150 degrees is able to give up heat, so that when it comes back in there through an expansion valve, it re-expands the refrigerant, and it gets very cold, about 40 degrees, which is what gives us our 72-degree indoor comfortable air temperature. So, a little keys to the kingdom. Ratings are so important, and the industry has so many ratings it can be very confusing. So let's get back down to basics. Everybody talks about BTUs. 1 BTU is the same energy as 1 wooden matchstick burned from top to bottom. 1 BTU is also exactly what it takes to take a 16-ounce bottle of water and raise it from 75 to 76 degrees. That's 1 BTU. So if I were to apply 1 watt of energy to this bottle of water at 75 degrees, 1 watt is equal to 3.4 BTUs, so it would now assume a 78.4 degree temperature. So that gives you an idea how we rate the heat movement, and it goes both ways. Heat is interesting in that there's either heat or absence of heat or removal of heat, and that's the way everything works in the industry with heat movement. So I have a very sticky thing there. So coefficient of performance, you'll hear air conditioners often rated in energy efficiency rating, which is the net cooling capacity in BTUs divided by the applied energy in watts. That's a really tough equation for most people. What's easier and what is used internationally is COP. COP stands for coefficient of performance, and it is just the energy delivered divided by the energy used. So if you deliver 36,000 BTUs of energy and you use 12,000 BTUs to do that, You divide it, and that's a 3.0 COP. It also works if you want to do it with watts. If you're delivering 1 kilowatt of energy and you're getting 3 kilowatts of heat, that's a 3.0 COP. Kind of like this right here. If you give the space heater that somebody in your office undoubtedly uses under their desk, and you take that space heater and you deliver 1 kilowatt of electricity through that cord to that space heater, it's going to deliver exactly, with mathematical certainty, 3,412 BTUs of energy because of that equation we just talked about. However, if you take that same kilowatt of energy and you give it to a geothermal heat pump that has a good heat source, that 1 kilowatt of energy is not going to be burned to make heat. It's going to run a motor. It's going to run a compressor. It's going to run a fan. It's going to run a pump. And for 1 kilowatt of energy, that motor, fan, and pump are going to pump 4 more units of energy from the ground and give you a grand total of 5 units of energy in the space, for a grand total of 17,060 BTUs at a 5.0 COP. So in this instance, it takes 20% of the electricity to deliver to deliver energy as compared to direct electric resistance heating. And that's the beauty of a heat pump. The number one naysay of electrification of our society, including the heating as well as cars and everything, but we're only talking about heating and cooling, is, oh my gosh, we don't have enough electrical capacity to do that. Well, I'm going to show you not only at this present snapshot do we have enough electrical capacity to turn on heat pumps everywhere, but we have probably more than enough electrical capacity after you see a future slide that I'm going to share. Going along with our Geothermal 101, this is such a simplistic way to look at it, because these are both carrier heat pumps. I am completely technology agnostic, so I just picked carrier on this one. Carrier has forever had splits like this heat pump you see here. Those refrigerant lines that go inside just connect to an air handler, and it provides heat in the winter and cooling in the summer. The only difference is it's immersed in the worst conditions possible for the work it's doing, isn't it? If you want heat, it might be below freezing outside. So it's a little harder to extract heat below freezing. So it works most of the time until you get down to those breakneck temperatures, minus something in the winter and in the summer, 100 plus. You're trying to reject heat to this outside air, and it's really hard. And that's the beauty of a geothermal heat pump. The outside unit, the condenser, is now replaced with pipes in the ground. And so if you consider at the example of the upper Midwest, the Northeast, it's between 50 and 55 year-round, the ground temperature. So you can extract heat all winter long from the ground at a much better efficiency rating than you can with an air source. And then in the summertime, you can reject that much cooler heat sink, which gives you a tremendous boost in efficiency year-round. And here's the thing, just a little sideline. Thermal storage. What happens around up to 20 feet around these boreholes is you get a little bit of a thermal battery effect. So after the end of the summer, you've been rejecting heat from all summer from your house down there. Guess what? The ground around that exchanger right there goes up about 10 degrees Fahrenheit on average. And it's not going to stay there for long because the mass of the earth is going to wick it away, but it's going to stay there for a good part of a season, and when you hit wintertime and you need heat, you can extract all that heat. It's like the heat you rejected in the summer is now available to help you with part of the winter. And that's what we call, that's the borehole thermal energy storage effect. And it's actually a science that is quite perfected. There are many commercial projects where we dump mad amounts of heat into the ground to use seasonally for the winter time. And the same thing, we can cold soak the ground for the summertime. Now, let's talk about some things about geothermal and thermal energy networks that that people don't usually think about. The first thing people want to ask you when you develop a new product is they want to ask you, what's my ROI? And I've always told my salesmen, do not answer that question until they understand all the other benefits of a geothermal heat pump. I say these are the things you tell them about first, because these are usually the things that help a customer make the decision. You have no more outdoor equipment, no more cooling towers, no more outdoor condensers, no more anything outside unless you want it out there. So you eliminate outdoor equipment, and because you eliminate outdoor equipment, you have a more hurricane and storm resilient building. And because you have a more hurricane and storm resilient building with equipment inside, your equipment is going to last about 2 to 2.5 times longer than standard air source equipment, simply because it's being so weathered and so extreme in its work in the middle of the summer and its work in the middle of the winter. Obviously, the solution eliminates combustion boilers and cooling towers and furnaces, which fits our decarbonization and reduction of pollution. It has noticeably superior comfort in both heating and cooling modes, because the heat sink is cooler in the summer and warmer in the winter, which gives it better, more even performance. You get remarkable system efficiency at standard equipment pricing. And this is what I would like you to focus on. These heat pumps here, just like you saw here, this heat pump, you can get a builder grade Carrier heat pump for the same price as you can get a builder grade geothermal heat pump. Few $1,000s, $5,000, whatever it is for an air source. A geothermal heat pump has no special technology necessarily. They certainly do come with some great options that we may get a chance to talk about, but it's just a heat pump. That's all it is. In this case, it's Carrier, York, Water Furnace, Climate Master, Enertech. It doesn't matter. They all make an extended range heat pump water source line. So when you look at the big picture, these energy networks can go in a lot of different ways. You can see here they've got some thermal storage. You can see here it's a lake source, surface water source, and sink for this building. They have a heat transfer building here. This is very similar to what they do in Ontario right now, and they're able to cool all of downtown with their lake source cooling off of Lake Ontario. And then they deliver this ambient temperature fluid here, in other words, lake temperature, to these heat pumps, and they distribute them through these buildings, and that's the essence of a thermal energy network. Just to give some examples, this is West Union, Iowa. They put in their thermal energy network in about 2011 while they were doing their city water lines at the same time. And this is 442-inch lines that go to the New World Trade Center from the Hudson River and provide heat sink to help that building get rid of heat. This is what and we're going to talk more about it, this is what a thermal energy network distribution line looks like. And these two taps go to a building, maybe a 300-unit apartment building, probably about 600 tons in capacity, and they are the beginning of what's called a decoupled secondary circuit, where you pull water inside the building. They have the pumps that pulls water from this constantly circulating energy network into the building. They either take heat from it or put heat into it, put it back into the other one, and it keeps moving down the line, hopefully to give heat to another building or having used heat from another building. Now we get to get a little bit more Jetson age on this stuff. So what we have here is, this is wastewater energy transfer development. These two buildings, these two 21-story buildings in the Bronx in New York City, they have, you can see the cooling tower up here. They have an absorption chiller in the basement, and they use Con Ed steam. Actually, it's not Con Ed steam. They have a local steam plant for their complex, but they use steam to drive an absorption chiller right now. What they're going to do is they're going to put in central heat pumps, and they're putting in a wastewater energy transfer system that is going to strip out all of the heat from the wastewater from these 316 apartments, and it's going to put that heat back into the building for use and this is an inaccurate representation of what we're really doing. This shows water to air heat pumps. We're doing that, but we're also doing all the domestic hot water for the building. That's the primary purpose of this, because we've proven over and over again scientifically in our studies that and Shark, who is here at the conference, Shark is the wastewater energy transfer company that's here. They see regularly that when they spec one of these, whether it's for a city center or for an individual building, they will get easily enough heat to take all of their domestic hot water off combustion heating and a good bit more. And here's the thing, when you do this, you don't only get the heat available for domestic hot water. 65 to 75 degree temperature is a great heat sink, so it gives you a long way toward your cooling load in the summertime. So we won a what's called the Empire Building Challenge Award for this design because we said, let's do it this way. You know, it's kind of like a narrative. We propose that why don't we, instead of drilling holes first, because there isn't an energy network on these buildings yet, there is one planned, but we said, why, before drilling holes, why don't we propose to do everything we can with wastewater energy transfer first, and whatever the balance is, we will drill the boreholes to make up the difference. And so what that's essentially saying, and NYSERDA, the New York State Energy Research and Development Authority, loved it. And they said, this is a great idea because we are giving them a non-intrusive solution to start decarbonization. Before they ever drill the first hole outside, they can start extracting heat from systems in their building and start on the road to a geothermal heat pump building or community just by putting in the wastewater. So in other words, when you did this, it doesn't mean you get to take off the cooling tower and take out the combustion yet, because you may need more capacity, and you will. But once we do, that gets them part of the way decarbonized. 30% is an incredible amount, and in this case it's more like 45%. And then we're going to put in boreholes for the balance. Now, part of the reason for the strategic effort on this is we actually know that there's a thermal energy network coming through, and they will probably end up tying into that and not have to do the boreholes. So this gives us a little delay time to say, let's get the first part done, and maybe by the time we get done with the wastewater energy transfer on these buildings, the thermal energy network plans will be there. So this is from West Union. You know how I said they did it at the same time as the water lines? You can see a new water line coming into this. They had to do this to all the buildings downtown. And then they have 2 geothermal lines coming off of there. And they just stubbed them into every building, kind of like you would do with natural gas. When they first came through, a lot of the clients, when the natural gas came down the street, they stubbed, or they put the box out there and they go, well, what am I going to do with that? And then one day, their oil furnace or whatever they had went out, and the gas company says, yeah, we'll help you put in a natural gas furnace, and then you'll be spending a lot less on fuel. It's cleaner burning, and that's essentially what they did. So this is kind of what's happening in the geothermal world with these thermal energy networks. We're stubbing into all these buildings, and this is called the carrot method, and we're saying, yeah, the IRA has huge benefits. You can put in a heat pump on this system and save 30, 40, 50% on that, and you don't have to drill a well, because we've already done that part, and all you have to do is hook to it. It makes a geothermal heat pump, it makes air conditioning and heating an appliance level industry. When I say that, hooking up a heat pump is fundamentally, not literally, but fundamentally as simple as putting in a washing machine or a dishwasher. You've got to put electric to those 2 appliances, and you've got to connect 2 hoses. Same thing with a heat pump. And it takes that outside refrigeration, you know, tying in those refrigerant lines out of it. So here's where the rubber meets the road. In 2010, at the ASHRAE building at their headquarters in Atlanta, they said, let's stop the bickering. Let's put in the best VRF systems the industry has to offer. Let's put them in the first floor. That's the air source heat pumps. And let's take the best geothermal heat pumps the industry had to offer. It happened to be Climate Master in this situation. They were just 2-stage heat pumps, 2-stage scroll compressors. That's all they were, extended range heat pumps. So the blue lines here indicate the corrected energy use per square foot, and the red for geothermal, and the red lines indicate the corrected energy use per square foot for the air source heat pumps. It's kind of interesting to look at the fact that the geothermal heat pumps are doing their job, and this is Atlanta where the ground temperature is about 65 degrees, and so they're doing their job pretty darn good here, and they're showing their colors and saying, yeah, we're more efficient than air source heat pumps in the summertime. But here's where the difference, here's where the rubber hits the road. In the wintertime, when you need heat the most, the geothermal heat pumps are saying, dude, this is easy. I don't even need as much energy as I was using in the summertime. So what does that tell you? That tells you that whatever we're using in electrical consumption, demand for cooling in the summertime should be less for the heating in the wintertime if it's properly engineered. So the next time you hear somebody say, where are we going to get all of the infrastructure, the electrical infrastructure to electrify our buildings? We're going to blow up the grid by a factor of 3. We saw what happened in Texas in 2021, and everybody's scared to death it's going to happen to them. Well, not so. That's why people will ask me and say, Jay, why is the federal government and the state government putting so many subsidies into geothermal heat pumps? What is the deal here? What's wrong with air source heat pumps? And I tell them this story, and I'm going to tell you a factoid that can be proven out with several reports, including the new DOE geothermal heat pump report that came out in December of 2023. What I'm here to tell you is that they know that for every dollar subsidy that they put into geothermal heat pump implementation, they're going to save $3 in electrical infrastructure upgrades. Electrical infrastructure upgrades are very costly. They're not cheap. It's much cheaper, as I just said, $1. You see all the subsidies coming out, and we're going to have some slides about those subsidies in a little bit. But this is big. This is why there is so much heavy investment by the federal. It's a one-time thing too, in that once the infrastructure is in, what do we have? Permanent infrastructure. It's like a water line. It's like a sewer line. It's like putting the electrical underground. It no longer can get blown down, and ice storms don't hurt it. So we're putting in infrastructure that's going to last arguably as long as 300 years, because the base material for energy networks is high-density polyethylene. So here's 2 buildings in Oklahoma, completely different test done by Climate Master. 2 identical office buildings. One had VAV type air source heat pumps, the best they could get at the time, and this is back just before 2010. And then they put geothermal heat pumps in the other building. It's fascinating to look at that flat line. It doesn't even care what the temperature is outside. While the air source heat pumps are screaming for relief, the geothermal heat pumps are over here going, what? It's nice. My source is nice. I don't really need that much energy at all. And that's what it's doing to electrical companies like National Grid, where right now they're peaking in electrical consumption in the middle of the summertime, June, July, August. Their natural gas in the kind of pink color here is peaking when? In the winter, when they're using all their natural gas. So the electric companies stand to really maximize the output of their grid, because it flattens it, just like you see here, where they weren't using much electricity or selling much electricity in the wintertime. In the wintertime. Now they're selling almost as much electricity as they are in the summertime. So that's a beautiful thing. Here's another reason why the wholesale implementation of air source heat pumps might get a little troublesome. It just might. You know, I like graffiti. Some people consider it art. I didn't know you could have air conditioners and graffiti become art, but you can do that. But here's the other thing. I have done some hair. I'm a contractor. I grew up, cut my teeth installing these things. And there's an extension ladder bolted right there. It's probably got a safety cable. I got to tell you, can you imagine trying to replace one of those compressors, Jeremy? No. You'd have to get me a bucket lift over there. I'm too old for that crap. Anyway, and then what about this? Technically, it might I don't, it's like they started and said, yeah, just, it looks pretty good for my house. I think that's square. I don't know. But that's, you know what, unfortunately, appliance level air conditioners, the 9,000 to 24,000 BTU mini splits, can be put in. When I say this, a lot of jurisdictions don't even require a license to put in these things. Those that do, people that are putting them in don't care. They put them in overnight or early in the morning. If they get red tagged, they just go pay the fee. I know. I used to bail people out all the time. Jay, I got a red tag. Well, what's wrong with it? Are you going to fix it? I don't have a license. Oh, bummer for you. You need me to fix your problem? Yeah, I need you to fix my problem. My customer won't pay me until I get this red tag off. And so, you know, and this is what's happening. I don't know if this company was licensed or all these companies probably in India were licensed. I don't know if any of this was licensed, but I just know the inspectors can only catch about 1 in 100 non-licensed activity situations like this. So how big is this all getting? Standard & Poor's interviewed a whole bunch of people, and we were privileged to be one of those they entered, and they said about thermal energy networks, they said efforts to develop centralized community geothermal heat pumps expand in John Murphy, he's a union brother, and Lisa Dix. I forgot that was who wrote it, or yeah, it's an op-ed, it looks like. Bottom line is, this is that was one, that's a different one. I just realized I don't even know my own slides, do I? That's one article right there. This is another one by Standard & Poor's. I love this one though, because it says, in this article, it says this is the last great frontier for energy companies to capitalize. The Con Eds, the Southern California Edisons, the National Grids, the Eversource, they are not monetizing right now the waste heat coming off of buildings, right? Now, because thermal, and just to give you up to date, 3 states have passed legislation to make it possible for PSC regulated utilities to sell energy they did not create. 13 or 14 states are in process of passing that kind of legislation, and there is federal legislation that was introduced by Senator Klobuchar in Minnesota that hopefully will make this across-the-board thing. So the states will stop having to worry about doing. They can adopt that federal legislation if they want. So it's just making it so that, like Con Ed, it's such a funny thing. Con Ed is saying, so you want me to take the energy off of them, run it over to here, and who do I charge for that? And that's the thing they're working on, the vehicles for charging, because when we talk to the posts, I'll show you. This is a great, yeah, I'm going to tell a story while we talk about this. This was created for a kind of a cutaway of what a New York street would look like. But when a cooling dominant building is dumping energy, they're able to turn off their cooling towers essentially. Now when you turn off your cooling towers, you save energy, right? Because you're not running those fans and pumps necessarily. You're also saving on chemical maintenance, which is can be pretty rigorous and expensive. So when we talk to, for example, a post office, I'll show you in a future slide here, they said, so you're going to give us something, and it took a long time to get a sit down with them. They said, you're going to make it so our cooling towers, we don't have to run them all year long. And we said, yes, we want to use the heat that's going out of your cooling towers and bring it to Penn South, the adjacent complex, and we want to dump it into those apartment buildings so that they will have a heat source rather than having to drill geothermal boreholes. And in this, before we move on, you can see they've got the subway, they've got the wastewater heat recovery system grabbing the heat from the wastewater lines. They have intermittent and green spaces. They'll throw in geothermal loops to balance the field, and it doesn't show the water here, but they can dump it in the water. And kind of what you're looking at here, and the key is if it's brown, it's obsolete and they don't need it anymore. They still need some fresh air, so you see fresh air units up here and so forth that need to be conditioned, but they can also be connected to the thermal energy network. Now, lest you think, or me, every day I learn a new way to hybridize geothermal. at the Cornell campus in Ithaca, they have a really novel way, because you think of geothermal as either that hot geothermal that creates electricity, or maybe even deep direct use like Old Faithful, or like we've been talking about mostly here, which is the low temperature geothermal exchange. Well, Cornell did something really cool. They're right next to Lake Cayuga, which is a pretty deep lake, a couple 300 feet, and it's all year long, it's 40 degrees at the bottom of that lake. So they put pickup lines there, built a little lake source cooling building here, and guess what? Because that's so cool, they get, like Jeremy has at his shop, they get passive cooling all year long. They don't even need to run chillers necessarily. While they have them there for backup, they're dumping all their heat into the lake. That's geothermal cooling at its finest. I mean, it doesn't get much better than that, because you don't even have to run a compressor for that. The only thing you need is good heat transfer fluid in there to make sure your system doesn't gum up, and it's going to run forever. And they've been creating their own electricity through a combined heat and power plant basically since the 70s. And they're doing it fairly clean. The best use of natural gas as far as considering emissions is to run a natural gas powered generator, because it's a pretty good use of natural gas when you look at the emissions. I'm not saying it's the solution, but they've been using this since the 70s, and they want to idle this down, so they're drilling, and it's never been done before in New York, because it's not known as a hot geothermal territory. It's not like Nevada, and it's not like a lot of places in California. So they've drilled a 4 to 6 kilometer borehole. They've gotten down to where they've got enough direct evidence of enough direct heat. They could at least provide the raw heat, the hydronic heat for this loop. What they would really like to do, I don't think they're going to get there, is they'd like to find enough high quality heat, meaning heat in the 500 degree range, which they're down around, they're hitting close to 200 now. And I'm not a geologist, so I don't know how far. That's really their dream, though. They would love to make their own electricity too. It would be epic, because nobody's tried to do it. It's like drilling for gold, digging for gold really deep, when your friend over here is picking it up off of the shore of the river, and he's getting a lot more than you, and they're just kind of like, but they really want to do this. They have all this free heat, but they really want to get the electricity too. They could hook up to the grid, and they may have to, but this is a story in process, so you're brought up to date. But look at that. They're using 2 different sources and sinks to make that happen. Now, Cornell on Roosevelt Island in New York City built this in 2016, and they built this geothermal field right out in the grassy area here, and they completely heat and cool that building. They use radiant cooling like Jeremy has in his place at 455. They use radiant heating in the floors, so it's almost all hydronic, very, very little energy consumption for energy distribution. And they had another great benefit in this one. Once again, I've never seen another one quite like this. They had such a big fracture in the granite down below here, and they're right up against the Hudson here, and they had such a big fracture in the granite that they were directly communicating with the river. And since they were directly communicating with the river, they realized they could put in what's called an annulus pumping system, which, if they get beyond the capacity of the boreholes that you can see here, they just turn on a pump that's on the surface, and it forces water through those and it gives it fresh water straight from the river. So they have a closed loop, open loop hybrid, right? And it's like, and Rick knows this, every time you get to another job, if you put your thinking cap on, you're going to find another way to really maximize their capabilities. Love this one, but this wastewater energy transfer system here is just amazing. You're taking that wastewater and all those dollars you paid to heat the water from whatever it's coming in at, 40 or 50 degrees, to 65 to 70 degrees. All we're doing is stripping that heat out and making it so we're not paying for energy twice. We're able to reuse that energy we already paid for, and you already saw that example. Down, when you consider your streets when you're doing these thermal energy networks, a lot of people go, okay, we're going to have big pipes moving energy through the streets. How do you access those? What do you do? These are images from our friends across the Atlantic of vaults with pumping centers and exchangers that they just put right down under the streets or in the right-of-way. It makes it so they can go in the buildings, in the basements of strategic buildings, but they can also go in vaults and just be dropped in, and people can jump down manholes and work on them. This is a district-level energy, wastewater energy transfer system. You can see the access holes here and so forth. And this is it from Canada. They're actually putting in the tap for the wastewater main there to extract the energy and put it back in. And so what happens is all we're doing is tapping major utilities wherever we can and saying, let's grab that energy and put it back into the thermal energy network. And look how sweet that is. You can see, if you could see all this, there are diversion pipelines coming out here where they can pull the whatever spec amount of energy or wastewater they need to out of the stream without messing with the stream and use what they want to. Pretty fantastic. So what I want to do for people like me, I'm 10 years old at heart. And if you can't tell by my slides, I like to make pictures of everything. And this is actually, you recognize that. This is from the last time I was here with the pipe fitters in, I would say it was 2020. We were doing a train the trainer on thermal energy networks. And I took this picture myself of all the energy coming off of the buildings. I think it was in January there at that particular time. And what we do is we turn off those cooling towers, we pipe that energy hydronically over to the apartments and buildings that need them. One picture tells 1,000 words. You can turn off those boilers, you can turn off those furnaces and replace them with heat pumps. Now, here's an example of what we did at Penn South in right near Penn Station in New York City. This is 15 22-story buildings in this 5-block area right here. They have a central energy plant right here with central chillers for cooling that use a cooling tower and central boilers. They need 5 megawatts of thermal energy to heat 2,500, almost 3,000 apartment buildings. And so the question, again, it's interesting how sometimes these state agencies do this. The RFP went out and it said, or RFI said, how can we heat all these buildings and turn off the combustion heat at that central energy plant with the least amount of infrastructure difficulty, drilling, cost, and everything? So we put our engineers and scientists to work, and they found that the post office across the street, that's the main sorting station for Manhattan, it's a pretty big place. You can't really, I mean, if you think about the fact that this is 5 blocks and this takes up this, it has 8 megawatts of thermal energy rejection through its cooling towers all year long, even on the coldest day of the winter. So we said, if you let us pipe the energy right over here to this central energy plant, we'll replace one of those boilers with a 5 megawatt heat pump, and we will take all that energy, that 8 megawatts of energy, and we'll use as much of it as we can to turn off. And they have a hydronic, 4-pipe hydronic distribution system to all these buildings. And so all we got to do is do that at the central plant, and they've stopped all that combustion heating. Of course, and we don't win them all by a long shot, but we won another award on that one because they said, this is a great idea. They said, who else can you get on the bandwagon? We talked to the SUNY, the State University of New York Fashion Institute. We talked to several people, and you can see them, Tishman Spire, Holy Apostles Church, another church, and some other buildings. And so we got ourselves together a thermal energy network. And that's how it happens. And this is, you know, this stuff can get pretty big and pretty messy. A couple of our initial, and we would use local union labor to price the pipe fitting and everything. A couple of these things like that one right there at Penn South, just what you see there for those few buildings and everything, because of all the, if you've ever, even seen a hole opened in a New York City street, oh my gosh. They don't even know what's there until they open it up, and they have to really carefully, and then you got to find the room for the piping. And so it was a $250 million job. $250 million for the infrastructure for this. And there's more to it than this. We went a little further, but this is just to keep it simple. So, but it's only one time. Once it's in, and we have enough. And so the way they do it is we do a bunch of small thermal energy networks that have thermal coupling to other thermal energy networks, so we can actually handle distribution between energy networks. This is that one amalgamated facility in, there's where those two towers were, where we're doing the wastewater energy transfer. And the actual amalgamated complex, it makes a triangle up here. It's got a lot more. That's the two towers there. It's got a lot more to it. And then on the way around Jerome Park Reservoir, they've got DeWitt High School, the Bronx School of Science, Lehman College, Discovery High School. And so this is a thermal energy network that we propose to tie the two towers together. Remember how I said, okay, if we just do wastewater energy transfer, we're going to need to drill some boreholes to get the rest of the energy transferred. But we said, but wait, there's more. If you let us tie in with these high schools and other buildings, they have a lot of green space. We can put the boreholes there if we want to. We could even, this particular reservoir comes from Upper New York. It's part of their big drinking water system, that aqueduct project they did. And they run a third of about 1 billion gallons of drinking water a day through this. I don't even want to tell you how many tons that equals. It is astronomical. So right now, codes don't allow drinking water energy transfer in New York City. We're working on it in Minnesota for right now. But just to talk to you about where 2 years ago, you couldn't sell thermal energy that you didn't create. Now we can do that. Drinking water is the next hurdle because, like wastewater, we always have drinking water going through our buildings too. And drinking water, just think about it like the water cooler out front here. All we're doing is we're transferring heat from a refrigeration system to drinking water through a double wall heat exchanger. That's the way drinking fountains and ice machines do it. We just want to do it on a utility scale like they did in Ontario 17 years ago when they decided to use all the drinking water they pumped from Lake Ontario as cooling water too. They run them through exchangers. The cooling loop is separate from the drinking water loop, but at the same time as they're providing all their drinking water in Ontario, they're providing all the cooling capacity they need for Ontario in the summertime. And that's the smart way to do it. So I've mentioned, and it's worth reading here, when we're talking about water energy, there's another type of hydropower. It has to do with using the movement of water to transfer the energy in the form of BTUs. It's one of the most basic and simple uses of water in every form. It has been safely done for generations and has been legislated as the recommended form of heating and cooling energy transfer. In other words, if you ever think that it uses less energy, DX is a necessary refrigeration principle, direct exchange. It can be left almost every time just in the refrigeration box in which the cooling's done. The distribution is always more efficient, moving energy in the form of hydrothermal. You move it, you move BTUs in water, it uses less energy per BTU than any other way of moving it. This is an image. This is just a bunch of ways you can use existing infrastructure. This is an image of the Ontario Deep Lake Water Cooling System. This is an image of one of the suggestions to do the food processing facilities in New York City using a river water exchange here. This is, subways, they're actually doing this now in New York. They have to dewater the subways to the tune of tens of millions of gallons per minute throughout the city at hundreds of different locations. They just dewater the subways and dump it into the rivers, and you can kind of see this is just one of the manholes. We're now starting to divert that through geothermal heat pumps so that we don't even, it's already being done. It doesn't even require any more effort. So this is really good. I don't have time to explain it, but it's a really good rationale for why water energy will be a big thing coming up. This just shows the hybridization of a geothermal or a thermal energy network. It doesn't matter whether you're using open loop wells, closed loop wells, surface water exchange, wastewater exchange, drinking water exchange. You can use any type of exchange infrastructure that is available and not forbidden by the AHJs. This is a university, and this is really important. If I didn't get time to show you anything more than this, I want to show you this, because this is a kind of spread out university campus, NYIT in Long Island. And so they ended up with 3 clusters of buildings. And you can see right here, if you look at the purple, one cluster has about 850 tons, another 740 tons, another 215 tons. So those clusters do their own thermal energy network. And then if they have an imbalance that another cluster can use, they go through what we call a transportation loop, a thermal transportation loop, where you dump or absorb heat from another cluster that you might need for another loop. Now there's one given. In the middle of the winter, you can have great diversity of loads. That means heating and cooling going on at the same time. In the middle of summer, everybody wants to get rid of heat. Everything is rejecting heat. So we always build these things. We have no problem handling the heating load internally in a thermal energy network, where we have our biggest lift is finding out where to put all that energy. And Ralph Ferry, if you don't know him, I'm so glad he's here today. He's got more patents than I am years old. And he runs Multi-Aqua, and he is working on, and I've known this is coming, but he's working on a technology to make low-grade heat convert straight to electricity. I mean, I'm talking 100 degrees, 80, 90 degrees, convert straight to electricity. And the proof is in the pudding. He's a manufacturer that most of his products are, he sells to Train Carrier and the like as part of their packages on equipment. So he has got just some really remarkable ideas. As a matter of fact, he's the first person to come up with what's called a multi-source heat pump, which does both air source and ground source at the same time, but either or any way you want it, which really optimizes your capabilities in a heat pump, because when you're in the shoulder seasons, you want to use air source. It's just a good heat source and heat sink. When you're in the extremes, you want to use the ground source. So that's just a little more about those. Mimi, who is in the back, has some flyers for the Thermal Energy Networks symposium coming up in Rochester, Minnesota, and you're going to hear a lot about they're doing thermal energy networks for the Mayo Clinic and for the downtown district, and that is Jeremy's home state, and he'll be there. We're having we're really, what it is city and government leaders that are trying, and believe me, it's overwhelming right now, that are trying to initiate thermal energy networks in their little cities and states and communities nationwide, are coming at us, meaning the industry, faster than we can answer the calls right now. So this is a place for people to come and listen to the facilities managers, the engineers, the architects, the utilities, RPU, Rochester Public Utilities, will be there talking about how they came together to start expanding network, and how the IRA is paying mad amounts of money to fund these things. And while I don't have a lot of time to cover it, you can see a lot of the modeling that's gone into their projects there. This is kind of interesting. This is a scientist's flow chart to show how everything communicates thermally in a very large thermal energy network, because it's way beyond my pay grade, so that's why we have good people working for us handling it. In addition to that, and this is where I'm going to finish since I'm at the top of the hour, we have a lot of arms at our company, and one of them is that we sit on the technical committee for the IATMO Uniform Mechanical Code. We've been instrumental in the 2024 Geothermal Energy Appendix. in the UMC, and a lot of other things. And in addition to that, we're very much into education. We've written several, as well as we have a couple of McGraw-Hill books. You can just Google geothermal books, and you will find them on Amazon or anywhere. As a matter of fact, you can go to the ASHRAE bookstore here, right here. There's usually 2 locations, and they have these books there too. But Mimi is going to hand anybody that wants it. This is just published by some friends in, where Mimi? Sweden. It is a book about all the renewables written for kids. I mean, and it's so well illustrated, and these things cost $14.99 each, but we became an ambassador for them, and so we bought thousands of them, cases of them, because they're such a good read, and they're so good for kids. So everybody grab one on the way out. On the back, there's a little QR code where you can see how to order more if you want to. We don't make any money off them. It takes you straight to their website. We do, however, at the location on this QR code, we have downloadable kids books that include coloring books, and you can see the artist where we started from to get to where we are now with these books. And we just really want to say that we're out there to share the information. That's why we work with IATMO so closely, because they get our name out there and get the technology out there. And we want the younger generation to grow up with this as a second language. Oh, geothermal, sure, yeah. They won't have to know when they come up, well, is that a heat pump? Are you using a recip? All I know is it's geothermal. Keeps the lights on, keeps the house cool in the summertime and warm in the winter, and keeps the domestic hot water working. So that is my presentation for today. And I am, I don't know how backed up we are with the next session, but I'm not leaving till everybody's satisfied if they have any questions or comments or anything. So let's leave it there. Thank you. The ground source infrastructure, hey, by the way, that's my grandpa Theron Egg and his place in the 1930s. Isn't that cool? I'm in the business. Here you go. The ground source infrastructure can be whatever you want. As you can kind of see here, this building has got energy piles. That's one thing you could do. This building is, energy transfer station is tying into the aquifer, and it's pulling water from the aquifer. It's going through exchangers, and it's supplying what we call the thermal shock absorber, right, Rick? We want a bandwidth of 40 to 90 degrees in our loop, and if it gets below 40, we turn it on because the aquifer is, 50 degrees, and we start putting energy back into it. And if it's the summertime and it's above 90, we turn it back on because it's 15. It strips the energy out and dumps it right back into the aquifer. And of course, surface water energy transfer works like you see over here, surface water energy transfer. If you're near a lake or a river, of course, there are about 7 major types of geothermal infrastructure that is standalone like that can be implemented as we call it plug and play on a network. As you kind of see here, these buildings just plug in. I like Rick's presentation 2 days ago, because you see how these are 2 arms for each building connecting to a network. Rick told everybody in the room, put your hands in front of you. He said, you are now part of a thermal energy network. That's what these buildings are doing. 2 arms coming out, now they're part of it. It's a decoupled secondary circuit. And it's proven. These systems are going in all over the world and all over the United States now. That's a great question, and I want to answer that. Ralph, once again, he knows, because we've been really going back and forth with the city of Rochester about this, because they have, on the outskirts of the city, these neighborhoods. It might be 10 years before the energy networks come through, but in the meantime, their furnaces are failing. They're neighborhoods from the 70s and 80s, and their furnaces are going out. And what they say is they can't afford to have one more person who has had a furnace fail put in a new furnace, because how long does that take them out of the solution side of the equation? They're going to have that furnace for another 20, 30 years, right? So they need a solution that's hybrid. And to answer your question, I think it's too expensive and too much trouble to drill oftentimes a single borehole for a single house. It might be better to put in a heat pump, a geothermal heat pump in your house that has a component of air source heating and cooling, so that, and those are coming out this year. They're being unveiled. Ralph has a line of them. Water Furnace has a line of them now, it's so new. I haven't even put it on the slides, but you will be able to put in an air source heat pump like everybody else. Then when your energy network comes through, you tie into it and you're none the poorer for it. And Uncle Sam, you've saved a lot of money for the taxpayers of the United States, because you could have put in your own borehole and it would contribute to the overall system. But honestly, it's always better to deal with the major infrastructure, because it's going to be less cost per ton to do it that way. And I've had many people over the years say, Jay, should I do this? It sounds, and I say, if you have the money, by all means. If it's putting you in a pinch, no, I wouldn't say, because eventually energy networks are coming through. And so I'm a little more practical about it, but I think I have another part to answer. I'm sorry about monologuing. I got one more thing. We have won 2 grants to take villages that have no access to natural gas, who are only using propane or oil, and they're suffering through energy poverty. I didn't even know this was going on. There's a village called Speedsville in New York, Upper West New York, and the average 1,500 to 2,000 square foot homeowner there spends $800 to $1,000 a month in the winter for fuel. The same one with a heat pump would spend a quarter of that. You saw the equation over there of electric. That's the same kind of equation you see when people are using propane. It costs about 4 times what it would cost to run a heat pump. So we're solving energy poverty, and the reason I'm bringing that up is NYSERDA in New York recognize that those are the people that need it even worse than the downtown areas, because that's energy poverty. Mimi just wrote an article about that for Plumbing Engineer. I'm so glad for the up-and-coming generation, because they have a new perspective. I don't think about energy. I didn't even know it cost that much to keep a house warm if you had propane in upstate New York. So, are we done, John? Should we be done? Wrap it up? Okay, I got to wrap it up. Otherwise, I think the next crew is coming in. Thank you, everybody. And grab a book on the way out.